Okay, so today we are going to be learning the difference between compounds, mixtures, and elements. So first of all, we're going to start off with the second 2.2, so the second unit in Chapter 2. First of all, we're going to talk about mixtures. So the important part on this slide is that mixtures are a physical blend. So if you are talking about physically combining things together, whether it be stirring, whether it be melting, whether it be evaporating, all of these are physical changes, so it results in a mixture. Okay, there are two different types of mixtures. The first one is called a heterogeneous mixture. These are mixtures that are not uniform in composition. So in other words, you can easily see the differences in them. So I like to use the example of Rocky Road ice cream. You have a little bit of marshmallows in there, you have some chocolate, you have some nuts. They're just all mixed together. So every bite is a little bit different. You can still see the marshmallows. You can still see the ice cream. It's just you're tasting them all at the same time. So another example would be a chocolate chip cookie. One cookie might have 4 chocolate chips in it. The next one might have 7. But you can easily see the chocolate versus the cookie part. The second type of the mixture is a homogeneous mixture. Now, sometimes it's pronounced homogeneous, but I say homogeneous. That's how I was taught. To me, homogeneous is in relation to pasteurization of milk. So I don't really care which way you say it. Anyhow, a homogeneous mixture is a mixture that has the same composition throughout. So when you're looking at it, you can't see any differences. So when you look at Kool-Aid, you can't see the Kool-Aid versus the water. It all appears to be the same thing. Even though it's still water and it's still Kool-Aid, you're just tasting them at the same time. Another name for a homogeneous mixture is something called a solution. These two terms can be used interchangeably. And then the important part of mixtures, and try to keep this in mind because when we get to compounds, we'll talk about this a little bit more, but mixtures keep their own properties. So, for instance, another type of solution is sweet tea. We all know what tea tastes like. We all know what sugar tastes like. When you put your sugar in your tea, you still taste tea, you still taste sugar, you're just tasting them at the same time. So they're retaining their own properties. Okay, so let's talk a little bit more about solutions. The reasons we call solutions homogeneous mixture is because, yes, they're technically still two different things, but you have to look at the molecular level. In order to see the differences and the things you're mixing together, you have to be able to look at their molecular level. You have to be able to look at their atoms. And no technology we have will let us see that microscopic. So it appears that they're all one thing just because we physically can't see the different parts. The second thing about solutions is, a lot of times whenever I say the term solution, you guys automatically think that I'm talking about liquids. Okay, so liquids are not the only types of solutions. You can actually have lots of different types of solutions. The most obvious type of solution that's often overlooked is a gas dissolved in a gas. This is around you all the time. Think about our atmosphere. In our atmosphere, we have oxygen, we have nitrogen, we have carbon dioxide, we have carbon monoxide. We have all these different types of gases dissolved in the atmosphere, but they're all gases. They're gases dissolved in gases. Another example is a gas dissolved in a liquid. Can anybody think of an example of a gas dissolved in a liquid?
Soda.
Soda. Okay, soda has carbon dioxide dissolved in it. That's why when you open it, you sometimes get the bubbles. All of the gas is trying to come out of solution really quick. And then last but not least is one called when you dissolve a solid in a solid. This we often do with metals. So, for instance, we all know what brass is, correct? Okay, brass is actually, I believe it's copper and zinc, I believe. I might be wrong about the zinc. But brass is, we basically just melt down copper, we melt down some zinc, we just mix it together, and then when it cools, it creates what appears to be a new metal, but it's still copper, it's still zinc, they're just mixed together. The good thing about a solid dissolved in a solid, or in this case something called an alloy, is that they have the strengths of both metals. So copper falls a little short because copper is actually kind of a weak metal. It's very malleable. We can bend it really easily. Zinc's a little bit stronger. So when you mix them together, we get a little bit stronger of a metal. Stainless steel is the same case. Okay, the next thing we're going to talk about is something called a phase. And you guys have all heard this term before. Oftentimes when I'll give you an object and I'll say, what is the phase of this? And you're just going to look at it and you can say solid, liquid, or gas, correct? Okay. And basically that term means the same thing, but when we're talking about mixtures, the term phase is used to describe any part of a sample with uniform composition of properties. So if I'm looking at a heterogeneous mixture of solids, I can say that it's in two phases because maybe it's made out of rocks and marbles. They're in two phases. We can see the differences. They're both solid, yes, but they're in two phases because we can distinguish between the two. So a homogeneous mixture consists of a single phase, which means it all looks the same. So when I have Kool-Aid, every single part of my Kool-Aid looks the same. If I have tea, every single part of my tea looks the same. If I have vanilla ice cream, it all looks like vanilla ice cream. A heterogeneous mixture consists of two or more phases. So this would be like your chocolate chip cookie or your Rocky Road ice cream. Or simply if you just take rocks and dump them in a bucket of water, you can clearly see the solid versus the liquid. Okay, so this is the hard part about mixtures is we have to figure out some way to separate them. Because remember, the definition of a mixture says that they are mixed together by physical changes, by physical properties. So technically the only way to separate them, to unmix them, is to use those same physical properties. Some of them are separated really, really easily. Like for instance, the first example I give you is rocks and marbles. Well, to separate rocks and marbles, you can just dump them out and go, make two piles. Let's put all the rocks in this pile, let's put all the marbles in this pile, and you're done. That's pretty easy, correct? A little bit harder is trying to separate iron filings from sulfur. Iron filings are actually really, really, really fine. They're almost in a powder form, and sulfur is in a powder form. So you can't just dump that out and separate it very easily. So, but iron is magnetic, correct? Yes, so we can use a magnet. If you take a magnet close to the mixture, all of the iron should stick to the magnet, and what's left behind is the sulfur. So that's one, but being magnetic is a physical property, so you're still using the physical properties. So the next way that we can separate mixtures is using something called filtration. In order for filtration to work, you have to have a difference in size. If the things are the same size, such as salt water, what happens when you run salt water through a piece of filter paper? What do you get? Salt water. Salt won't filter out because salt is the same size as the water molecules. So if you run salt water through filter paper, you get salt water. Okay, so that's not going to work. So in order for filtration to work, you have to have a difference in the size. So let's go back to our example of rocks water. In order to get our rocks separated from our water, we just can put them through a filter. The rocks will be left behind, the water will run through, and you're done. Some other examples of this would be like when you're panning for gold. You do it in a river or a stream. The water runs through it. The gold is left behind. Another example is coffee. Your parents put the coffee grinds in a filter paper. When the water mixes with the coffee, it makes coffee, but you don't want grinds in the coffee that you're going to drink, so the filter paper filters out the grinds. Okay? So, like what we were just talking about, we couldn't separate salt water because the sizes were the same. So we have to have other forms of separation. So the next form that we're going to talk about is something called chromatography. And there's lots of different types, but the type we're going to learn about is paper chromatography. And this is basically when you separate a homogeneous mixture. So if you look back there at the bulletin board by Tara, you can see that all of those are called, those round pieces of paper, I call them pinwheels. And last year, my chemistry kids just basically drew pictures on there with black ink. We added a solvent, water, and it separated all of the colors. So it started out as a mixture of black ink. It separated into all of the different colors, just like you see up here on the screen. We have a little bit of yellow, a little bit of pink, a little bit of blue, and then a little bit of green. But it all started out as black ink, and it all started out down here. So it traveled. So that's one way to separate a mixture. And then the third way to separate a mixture is called distillation. And this is actually how I would go about separating salt water. So if you look at the screen, we can see over here we have a beaker. Let's just, for the sake, let's say it's salt water. Over here we have salt water. So we have a combination of salt and water. We can't filter it out. We can't use paper chromatography, so we're going to use distillation. Water has a boiling point of 212. Salt has a boiling point of over 1,000. So they don't have remotely close to the same boiling points, correct? So what we're going to do is we are going to heat up our salt water. When it reaches 212 degrees, the water is going to evaporate and it's going to rise. It's going to be forced over into this chamber. As it leaves the fire, it's going to cool a little bit, and then over here you're going to get the water dripping down. Now, as long as our heat stays under 212 or under 1,000 degrees, our salt should not evaporate. And so after a while, all of the water will be gone, and the only thing left over here is going to be your salt. So we're using a physical property of boiling point to separate salt from water. A much more complicated version of this is what is done to purify ocean water into drinking water. This is also, has anyone ever boiled water on your stove at home and noticed how maybe you weren't watching and you boiled all the water off, and has anyone noticed what's left behind on the pan?
A white residue.
Kind of like a white residue. It's calcium and magnesium. Calcium's in our water because we have hard water. We can also see that on your shower heads in your shower, sometimes on your sinks. It's just this little white buildup. That's because it's in our water. Different boiling points. The water comes out, the calcium gets left behind. All right, so now we have done all about mixtures, so now let's focus on compounds and elements. First of all, we have to learn a new term called substances. On your homework, there's going to be a question that asks you to identify mixtures versus substances, right? Substances actually include two things. There are two types of substances. They are called elements or compounds. Okay, so what is an element? An element is the simplest kind of matter. So what I mean by the simplest kind of matter is it cannot be broken down any further. If we break an element down, we're going to break it down into protons, neutrons, and electrons. It's no longer going to be the element. It's no longer going to have those properties. So an element is the simplest form. Okay, compounds, on the other hand, are substances that can be broken down. However, the only way you can break them down is to go through a chemical reaction of some sort. So we have to do a chemical change. When you break the piece down into its individual pieces, they have completely different properties than the original compound. So remember when I was talking about the properties of mixtures, how they stay the same? The properties of compounds are completely different. And technically, compounds are made of two or more atoms, and again, they have to be chemically combined. You have to go through a chemical change. You cannot just stir them together. Okay, so let's kind of compare. We've talked about mixtures. Now we've talked about compounds. So let's kind of compare the two. Compounds are made of one kind of material, so they are all the same. So if I'm talking about a compound of salt, every single crystal that I pick up is going to be sodium and chlorine stuck together. Okay, mixtures, however, are made out of more than one type of material. So that would be like our ice cream. Ice cream is made out of milk and sugar and flavoring of some sort, depending on what type of ice cream you like. The second thing is compounds are usually made by a chemical change, whereas mixtures are just involving a physical change. You're changing the state of matter or how they're mixed together. And then thirdly, compounds have a definite composition. So every single salt crystal that you eat is going to be identical to every other salt crystal. Salt is salt is salt. Okay? Mixtures, however, sweet tea, every batch of sweet tea that you make might just be a little bit differently just because it's a mixture. It's not perfect. It's not a perfect science. It's not Sometimes when you make sweet tea at the restaurant, all the sugar sinks to the bottom, so the top of your sweet tea isn't as sweet as the bottom of your sweet tea. Okay? Okay, so let's give a little bit of practice about identifying these. So here is our first example. I want us to just make some observations. So what do you notice about this picture? They're spread apart. What else? They're all circles. They're all red. They're the same size. For the most part, these guys look identical, correct? So if I had to choose element, compound, mixture, which am I going to choose? Element. They're all one type of atom. Okay. So let's look at this new picture. Okay, let's make some observations. What do you notice about this guy?
Different colors.
We have two different colors. We have red circles. We have yellow circles. Two different sizes. The red circles are bigger than the yellow circles. Some of them are touching, right? So let's look. We have this guy is one red, two yellows. One red, two yellows. One red, two yellows. One red, two yellows. You guys seeing a pattern? Yes, even though they're made out of two things, they're all the same. So, element, compound, mixture. Compound. And the last one, what are some observations we see? We have red, we have yellow. None of them are touching. So, technically, we have two things not stuck together. So, this would be a mixture. All right, so let's talk about elements versus compounds for just a minute. Compounds can be broken down into simpler substances by chemical means, but elements cannot. Yesterday we talked about a chemical change a little bit. A chemical change is a change that produces matter with a different composition. So in other words, you are ending up with a completely different compound than what you started with. So the chemical formula has to be completely different. Whereas in a physical change, if you start with water and salt, you're ending with water and salt, it's just mixed together. This time we have to have a completely different composition. Okay, so the important part of this slide is over here on the right side of the screen where it says, heat and light are often evidence of a chemical change. In a few units, we're going to do chemical reactions, and you're going to go in the lab, you're going to do several chemical reactions, and you have to tell me how you knew a chemical reaction was taking place. Well, first of all, right off the bat, if it produces heat, if you touch it and it feels hot, or if it needs heat in order to get the reaction to take place, it's a chemical change. Okay, heat is a type of energy. Usually chemical changes require energy or release energy. Another type is light. We see this every day outside. The sun produces light. Okay, well, on the sun, a chemical reaction is taking place to release that light and to release that heat that we can now see and feel. Okay, that's why it's warmer during the day and not at night. Okay, so let's talk about properties of compounds. So I led into this a few times, but properties of compounds are completely different than those of their elements. I talked about this with mixtures, and then I talked about this a second ago with compounds. But due to the chemical change, the resulting compound has new and different properties. So let's take a look at table sugar. Carbon is your pencil lead. Hydrogen is a flammable gas. Oxygen is also a flammable gas that you inhale every day. Put them all together, and it makes your cookies sweet. That doesn't make sense, right? If you take the properties of the elements, the compound is completely different. Another one is sodium chloride, which is salt. Sodium is a very reactive metal. All you have to do to get it to react is put it in water. Chlorine is a toxic gas that we often use in warfare. So we take something that's explosive and something that's toxic, put them together, and we put them on our food every single day. Again, this compound has a completely different properties than those of their elements. and water. Hydrogen and oxygen, like I just said, are flammable gases. You put them together and it puts out fire? Interesting, right? But that's because compounds have a completely different set of properties than those of their elements. So here is a nice chart that would be helpful on your homework that you're going to do. Because today I'm going to ask you to try to start identifying some elements, some mixtures, some compounds. Some of them you'll know off the top of your head. Some of them you might have to look up. You probably don't know what ethanol is off the top of your head. So you might have to Google that really quick, but I'm sure you can figure it out real quick. But if you look at this chart, it'll kind of try to help you figure out what it is. So over here, you start off asking yourself, can it be separated by physical means? If the answer is yes, it's a mixture. Then you have to try to figure out, well, is the composition uniform? Look at it. Can you see the differences? If you can see the differences, then yes, it's a homogeneous mixture. If it's no, then it is a heterogeneous mixture. Okay, coming back over here, if you cannot separate it by physical means, that means it is a substance. And then you kind of have to ask yourself, can it be decomposed by ordinary chemical means? The question I like to ask is much simpler to that. I just say, is it on the periodic table? If it's on the periodic table, it's an element. If it's not on the periodic table, it is a compound. So salt is not up there, so therefore salt must be a compound. Okay, so we talked about this a little bit the other day because you guys have had 2 element quizzes so far, but there are 117 elements on the periodic table. Honestly, past number 109, those are lab created elements, so those we won't really deal with a whole lot in this class. But most elements have a symbol consisting of at least 1, maybe 2 letters. The first one is always capitalized, the second one is always lowercase. And then I'm sure you guys are super curious. After your quizzes, after studying those 35 elements, you have wondered, well, why in the world does sodium symbol Na and not So? Why in the world is potassium symbol K and not P? Why is gold Au, so on and so forth? Well, the reason for that is because some of the names come from the Latin or other languages. Often those elements were the ones that were discovered a long time ago. Gold has been around for a very, very, very long time. So has silver, so has sodium, so has lead, so has iron. All of these have been around for a long time. So when they were first discovered, Latin was probably the prominent language, and so they were given Latin names, and so our periodic table reflects that. So for instance, gold's Latin name is Aurelium, that's why it's Au. Iron's Latin name is ferrous, that's why it's Fe, so on and so forth. So on your test, hint, 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 when I ask you the question, how can we figure out which elements were discovered first, your answer is going to be when the symbol doesn't match the name. Okay, right off the bat, if the symbol does not match its name, it's probably because it matches its Latin name, which means it was probably discovered, one of the first ones discovered. All right, so we are done with notes, and actually what your homework is going to be today is on my website because the copy machine was broken. But you can download this on your website, and I want you to answer these in your notebook. Section 2.2 questions, numbers 1 through 4, and 2.3 questions 1 through 6. Again, they're on the website, so you can download them. Be sure that you skip section 2.1. We talked about that yesterday. Go ahead and move on to 2.2 and 2.3.
Beautiful day.